Tonight I'm going to talk to you about sound from both an animal and a human perspective. So who am I to start with? I am an evolutionary biologist. Alas, poor Yorick, he is extinct now. That's a Tasmanian tiger, just a cheap publicity shot, nothing relevant there. However, I'm also a science communicator, so I talk a lot. I'm a photographer, nerdy wanker self-portrait in Japan, everyone has to do it. And I'm a violinist. You might wonder, what's this got to do with sound, right? Well, a lot of these interests I have involve waves, light waves, sound waves. And as a biologist, I'm very interested in the structures that animals, including humans, use to detect waves out in the environment. And I'm going to talk tonight just about sound specifically. And if you think about a concert, okay, this was Birds of Tokyo and the Melbourne Symphony Orchestra. Weird mashup, I didn't think it would work. Turns out it was great. If you think about a concert like this, you've got voices, you've got guitars, violins, cellos, flutes, drums, piccolos. I apologise to any musicians here if I've missed your instrument. It's not because I hate it. Unless you play the triangle, that's not a real instrument, it's a shape. If you think about these concerts, right, there's all different instruments producing sounds all at the same time. Yet, just hearing it with our two ears, we can hear a violin from a guitar. We can tell the voices of the different singers in the band, even though everything's going on at the same time. And I'm really interested by the structures that allow us to do this. So, before we get too deep into it, well, what is sound? Essentially, it's a wave. Come on, it's Nerd Nite, Big Bang Theory. It had to come in here. I promise that's the last Sheldon Cooper. If we want to get a little bit more specific, sound is a vibration that propagates as a longitudinal acoustic wave through a medium like air or water. What the fuck does that look like, okay? Warning, okay, there's about to be physics explained by a biologist. This is a bad combination. Trust me, the student feedback surveys say that. I promise, I passed university physics and I'm going to keep this really simple. So, we have a speaker and sound is coming out of it in the direction of that arrow, okay? If you think about the speaker, sound's coming out, and when it does, this wave travels and it displaces the air particles. They're the blue things. Sometimes the air particles are sort of moderately spaced together, then they're really far apart, then they become really close together, and that pattern keeps repeating. It's a wave. And when the air molecules are at their furthest apart, we call it an expansion. The air has expanded. When they're closest together, we call that a compression. Think of it as a bit like a Mexican wave in a room full of people that have had a few too many beers, all right? You're going to get someone that takes a couple of seconds after their neighbour does the wave to actually realise it's their turn and do it. And then you get that person that gets a little bit antsy and they say as soon as the person next to them moves, they have to do the same thing. That's kind of what happens here. Sometimes the movement's further apart, sometimes it's closer together. But with a sound wave, it happens in a predictable way. A couple of things we need to know about sound waves. There are two characteristics I want to point out, basically. One is the amplitude, which I'm blocking. That's good. So that's just the height of the wave. And the other one is the wavelength. So pick two equal parts of the wave, let's say the compression. It's just the distance between those points. That's it. So why am I pointing out those two characteristics? They really affect how we perceive sound. So the amplitude of the sound wave is going to decide how loud is the sound, okay? And the frequency will give us the pitch of the sound, okay? And the frequency is just, for want of a more fancy equation, it's the speed of sound divided by the wavelength, okay? So it's how many waves happen in a second, how many of those wavelengths. So if you want high frequency, you've got a small wavelength, a small number on the bottom of the fraction. If you've got a large wavelength, you get a small frequency. That's it. High frequency, high pitch, low frequency, low pitch. So now we know that sound is a wave. How do we detect these vibrations that propagate through the air? For humans, it's pretty straightforward, and most mammal ears are the same as ours. Sound enters through the ear canal. It hits this tympanic membrane. Just think of it as like the top over a drum. It vibrates when something impacts it. And those sounds get transmitted to the cochlea. It's just like a curly tube, just like it looks. But the cochlea is really cool because that's actually where all of the action happens. And if you uncoil this tube, which this diagram hasn't done, but if you did, you would find that different parts of the cochlea, as you move along, are sensitive to different frequencies of sound. So at the base of the cochlea, we're sensitive to higher frequencies of sound, around 20,000 hertz for a human. And as you get towards the narrow tip, you get to the lower frequencies, around 200 hertz and right down to 20. So the entire way we hear, in terms of frequency, is when the sound waves hit that cochlea, different parts of it are excited depending on the frequency of that sound wave, and that sends electrical impulses to our brain that then processes the sound. It really is, it seems deceptively simple, but this is how it works. It's how, in a room full of voices, we can identify the voice of our partner or a family member or a friend. It's this system that allows us to hear the violin over all of the other string instruments in an orchestra, just because of the way the sound waves hit this and the different frequencies all at the same time. And I think it's pretty cool that our brains can identify just that narrow, unique sound amongst that whole rowdy soundscape. So what frequencies of sound can we hear? I know I've mentioned amplitude. I'm just going to focus on frequency because we've only got 20 minutes tonight. For humans, we hear about 20 to 20,000 hertz. Anything higher than 20,000 hertz we call ultrasound because, you know, everything's about us, so if we can't hear it, it's not sound anymore, it's ultrasound. If you think about dogs, right, who here has a dog? Yeah, whose dog hates really high-pitched noises? Mine certainly does. So dogs have about double the hearing range. They can hear up to 45,000 hertz, so they can hear much higher frequencies than we can. But if you think that's impressive, well, none of us have a patch on the porpoise. The porpoise can hear up to 150,000 hertz. So, you know, maybe there's a job for them as the ultrasound tech in your doctor's office. I don't know. So what about birds? Okay, we know birds communicate with sound a lot. Beautiful songs. Well, how do their ears work? It's actually pretty similar to a human. So sound enters the ear canal, hits this tympanum, and it again stimulates a cochlea. It's a slightly different looking cochlea, but it's the same principle. And they can hear about the same as a human, about 50 hertz up to 18,500. What about the things that birds eat? What about insects? Okay, how do they hear? Well, we all think insects are pretty weird, a lot of people do, right? Well, this is going to make it even worse, okay? Because their ears aren't on their head, all right? Some insects hear with their antennae. Some hear with their mouth. That's just messed up, right? Some actually hear with their knees, okay? Imagine that if you heard with your knee, all right? Some have ears just near their wings. Some it's on the abdomen, some it's on the thorax, all right? It's weird. And it gives a whole new meaning to the phrase, I'm all ears. They literally are all ears, okay? So what does an insect ear look like? Well, there's actually about 10 different types. I'm just going to pick 2. So first, let's look at the kind of ear that a fly has, a mosquito. So they hear with their antennae, right? An insect antennae are covered in literally tens of thousands of these tiny little sensory hairs called sensilla. And some are used for hearing. So a sound wave, the vibration propagates through the air, and then it impacts this sensory hair, and that sensory hair vibrates depending on the frequency of the sound, depending on the pitch. That sends a signal down the antenna, it stimulates some cells depending on the frequency, and that sends an electrical impulse to the insect's brain. Okay, so they're hearing with tiny little hairs. If you look at katydids, I'm going to move to this side for that one. So these are kind of like big crickets with really long antennae, and they're bright colours usually. So there's the guy that hears with their knees, all right? It's a similar thing. You've got something, it's not quite a hair, but it sticks out of the exoskeleton. Vibrations hit it, it causes this little plate to vibrate, cells get excited depending on the frequency of the sound, and the signal goes to the insect's brain, all right? Just to give you an idea of what an insect antenna looks like, so this is one under a scanning electron microscope. So these are the little sensory hairs, the sensilla. They're literally just 4 or 5 thousandths of a millimetre long, okay? They're tiny. You can't see them without this special microscope. Some detect smells, some detect taste, seems a bit weird. Some detect vibrations and sound, these little hairs, and there's little plate-like structures that detect stretches and vibrations as well. So it's sort of interesting that insects smell and hear with tiny little hairs. It's tiny. Yet one tiny little hair appears in my ears or nose, and suddenly my partner's got the trimmers out. Not those trimmers. Okay, she's not a psychopath. Sorry, Belle. So where do insects and spiders aren't insects, but we're going to include them anyway. So insects can hear anywhere from 20 hertz up to about 50,000, so kind of the same as your dog. All right. Spiders, they can hear about 100 to 10,000 hertz. So now I'm going to focus on just a few of these animals, and I'm going to focus on birds, because we all like birds. Who doesn't like bird calls? And we're going to focus on spiders. Yeah, okay. I know what you're thinking. This guy's weird. He likes spiders. So I'm going to tell you now how we go from having happy birds and spiders. I can see people grinning. I did not Photoshop that. Okay, that is the Hawaiian smiling spider. I think it's the next Batman villain. Joker better watch out. But I'm going to tell you now how about human-generated noise can take us from having happy spiders and happy birds. We generate a fuck ton of noise, basically, from aircraft, cars, jackhammers, our voices, you name it. And we end up with sad spiders and, well, angry birds. So just going back to our frequency map as a reminder, birds hear in about the same frequency range as us. Spiders are about half of that, the bottom half. And why might they be upset? Well, it turns out the frequencies of most human-generated noise is between 500 and 5,000 hertz, so right in the range where they hear really well. So we'll focus on the songbirds first, okay? Some songbirds actually don't mind human noises. They'll incorporate it into their song, kind of like, if the video works, like this lyrebird at Taronga Zoo. We'll have a listen. Okay, the sound's not quite loud enough for that, but he's actually mimicking the evacuation alarm when the lions got loose at Taronga Zoo. He thought that was a cool sound, waited till the visitors walked past, then started going, evacuate now, okay? Funnily enough, he was taken off display for a few months. So why is community noise a problem for birds? Well, most bird songs are in the range of 1,000 to 11,800 hertz, okay? So half of that range is impacted by anthropogenic noise. This 11,800 hertz, cool fact, that's a bird called the black Jacobin. It produces sounds that high. We don't even know if it can hear sounds at that higher frequency, okay? That's just weird. So researchers looked at blackbirds, okay? They like to sing a lot. And they decided to look at how the songs of the birds differ if they're impacted by anthropogenic noise or if they're not. And they found that birds that live in the forest, no anthropogenic noise, the average frequency of their song is about 1,800 hertz. Birds in the city, their average song frequency is about 2,300 hertz, which is above the average frequency of 2,200 for anthropogenic noise from traffic. And their calls are also louder. So basically they have to sing louder and shift their song to a higher frequency so it's less masked by the human-generated noise. So this is good, right? They can shift their song. But maybe it's not. The same researchers looked at another bird, the great tit. I'm pretty sure this is the only context where I can say great tits and not get a HR complaint, okay? It is the bird, I promise. And they looked at what traits are associated with lower frequency songs in these birds. So we know that these are the songs that are more heavily masked by urban noise, but they're also the songs that the males sing when the females are at the peak of their fertility. And males that sing lower frequency songs enjoy higher fidelity from the females. So yes, they can shift their songs to higher frequencies so it's less masked by the traffic noise, but their reproductive success drops. So now what about the things that the birds eat? What about the spiders? Okay, so the lower half of their hearing frequency is impacted by human-generated noise. Now I know what you're thinking. Some people are going, Chris, I've never heard a spider make a sound, mate. I don't think they talk, unless it's the Incy-Wincy spider, but he just went down the water spout. It's us that does the singing. So some spiders do actually produce sounds to attract a mate. So this is the ground-dwelling wolf spider. So let's have a listen to this. Maybe. Don't know if anyone can hear that. That scratchy, maybe. So apparently, if you're a female wolf spider, you find that scratching noise sexy, okay? That's the courtship song for them. It turns out that those scratching noises on the leaves are generated at between 100 and 2,000 hertz, right in the range where anthropogenic noise can mask them. So some researchers decided, well, let's be nice to the spiders. Let's play environmental noise in the background while they're trying to mate in a controlled laboratory condition and see what happens. The males still made those sounds, but fewer of their reproduction attempts were successful. So basically, airborne sounds that humans pollute the environment with affects the quality of these vibrations that the spiders are making through the vegetation to try and attract a mate. So basically, us noisy fuckwits are making it really hard for animals to communicate using sound. So why should we care? Yeah, most people like birds, but who doesn't want less spiders, okay? It's one less thing to squish in your bathroom in the middle of the night. It's all about ecosystems. So insects eat plants for energy, and then they're eaten by spiders or frogs for energy, and then they're eaten by things like snakes and lizards. And then comes the bird that ate the snake, that ate the frog, that ate the insect, that ate the plant in the top left corner of the diagram. And then eventually, the bird dies. It decomposes, and the nutrients go back into the soil and are eventually taken back up into the plants. That's the soil that we plant our crops in. The plants that generate the oxygen we breathe, the plants that we eat, the plants we feed to the animals that some people eat. So, you know, kind of important to humans, not just to the animal kingdom. So can the effects of this noise actually be reversed? Well, the answer is yes. So this is Berlin's Tegel Airport. It closed in November 2020 after operating for almost 60 years. And researchers had been looking at the singing behaviour of some birds, including these 5 near the airport. And they were looking at the songs. And over the 60 years that the airport was operating, they found that the birds that lived near the airport started singing earlier in the day than birds of the same species that lived in the forest, not impacted by noise. So they sung earlier, so their song wasn't masked by the sound of the aircraft once the airport opened up. Just 6 months after the airport closed, those same birds were singing later in the day, about the same time of day as the forest-dwelling birds had started singing. So in less than half a year, that behaviour reversed. So we can actually undo the impacts of noise pollution, but we need to stop spewing as much noise out into the environment, and we need to get better at putting up barriers to reduce some of that noise. So we've talked about how sound is a vibration, a good vibration, and I've completely ripped off a song title there. That was to give people a bit of a hint that what I was talking about was sound. We've talked about how we detect the sounds that are generated as squawks, squeals, symphonies and anything else. And I've talked to you a little bit about how our ability to pollute the environment is a massive threat to a lot of the animals that we all like to enjoy out in nature. And now I'm going to stop polluting this room with my sound waves so we can hear some of your questions. Thanks for listening. I've got Halo. That's your. Oh, that's mine. Okay. I get to keep the clicker. That's dangerous.
Yeah, it's on the house. Don't worry about it. Can I get some house lights so I can see these gorgeous faces, please? Thank you. Alrighty. Questions right at the front here.
Literally thinking about this yesterday on my walk along the creek. What are government, local government, state government doing to make Melbourne nicer for What
is the government rather doing to make Melbourne or their councils nicer for non-human animals?
Well, if you'd like the answer that I'd like to give, fuck all is pretty much the answer. So most of us have driven through the lovely, you go through a lot of the bridges when you're coming into Melbourne and you see the fancy beams that are meant to be an art installation, nice curves over the bridges. Those are barriers that were actually designed to reduce the noise escaping from the road into the surrounds. Admittedly, I think that was more about the apartment buildings than about the wildlife, but we'll take the win. To be honest, this isn't very high on the government's radar. Light pollution is, because it's something they can easily fix. You can change the spectrum, the colour spectrum of lights. You can change how intense the lights are at night. Sound, it's not really on their radar, to be honest, and it should be, but it's a big problem to fix, so it sort of gets, swept under the rug. It's a lumpy rug. Any conservation biologist will say that.
Right. Just here.
If you want to figure out what part of an animal or insect is its ear, how do you research it?
How do you figure out what part of an animal is its ear?
That's a great question. Look, if you're looking at something that... There are ways we can kind of tell, so you can...
I forgot to tell you, we fixed the sound.
Awesome. Thank you.
We'll play it after the question
Thanks,
time.
Emily. Thought I was getting attacked by an evacuation alarm then.
That'll tell you all
I
about
called the
their
bird a
ears.
liar. I thought it was coming back to get me. So, yeah, look, for insects, it's kind of interesting. So you can get these little electrodes and you can put it at the base of those sensory hairs and you can, play noises and see if you get a spike. So you can go, this detects vibration or not. If it's an insect like a cricket or something, and there are other types of cricket that data's been established in, honestly, if you've done it enough, you can look at those electron microscope images and you can look at characteristics of the hairs. So, for example, the hairs that do vibration, they've often got striations, they've got stripes down the length of them, so you can look at that and go, well, that's not taste and it's not smell, so there's a good chance that it's sound. I don't know how they figured out katydids and crickets here with their knees. That's just fucked up, to be honest. But, I'm sure it was an accidental discovery.
Right. Okay, I've got a few. I'll take the person over here first.
I've often wondered why mosquitoes haven't evolved to be silent.
Why didn't mosquitoes evolve to be silent?
Look, it's actually, the noise isn't anything that they can help. It's kind of like when you hear a hummingbird, the wing beats, they can't help that. We just call them a hummingbird. Insects don't flap their wings up and down. They sort of actually rotate it, so it creates these little vortices at the wingtips that keep them up. Interestingly on that, because of the frequency that mosquitoes beat their wings, you get that sort of high-pitched that really annoys us. Hummingbirds, on the other hand, the reason we find them quite pleasant to hear, the frequencies that their wings vibrate are actually very similar to the range of a violin. So it sounds sort of a bit musical to us.
Right, and I had... Okay. Yeah, one here, and then there's two at the back, and I'll get to you, I promise. So this one here first, please.
You mentioned the corpus has a huge range. Is the speed of sound in water different to the land?
I don't know how to paraphrase that.
Okay. So, does water travel? Does sound travel differently through water in air? Yes, it does. It travels slower, and it's a bit more muted. It's probably their higher frequencies. It's probably more about, because of the depths that they're swimming at, it's kind of like bats that use echolocation to navigate. The porpoises are probably, and it's not well described, but they're probably actually using sound to some extent to locate prey and to navigate. So they're not so much listening for calls, they'd be listening for sounds generated by other animals moving through the water. So they'd need a much wider range of hearing. It's quite possible they produce vocalisations at those higher frequencies as well. To be honest, there's so few of them around, it's really hard for people to study. We just sort of leave them alone because they're all critically endangered. If you play with stuff that's really abundant, people are quite happy. As soon as you I want to do research that involves intervening with an animal that's critically endangered, all of a sudden people get very antsy, understandably so.
Nick at the back.
Yeah, thanks, Chris. You've explained a number of things why the wattle birds around my house start before peak allotrachic, 5 or what have you in the dark. But what I'm wondering about is I also know that some birds live near things like waterfalls, which are noisy as well, naturally noisy, but they're also experiencing some of these sound events. They have to sing louder, etc., etc. So they seem to do it.
So basically, what about anthropogenic? Is that the word? Anthropogenic?
Yeah, community noise, most people say.
Made noises.
Yeah, the natural noises, they've been around longer than the species, probably. They've evolved to have their calls at frequencies and at volumes that get around that. So, yeah, they might call more loudly, but they'll probably, I haven't researched that, it probably hasn't been studied a lot, but you would expect that their songs are of a higher frequency because you'd want to get above the range of the average frequency at the waterfall. But to be honest, it's more about volume. So it's probably not going to so much be frequent. A little bit of frequency, it's probably more about the timing at which they sing.
Right, and we had one more up the back,
one.
all the way up here in the corner.
Has there been any studies on what the animals think? Can they discriminate that noise is noise, or do they think they're just surrounded by other animals that they're overall information?
I only heard about 80% of that question, sorry.
So I think it was due, and correct me if I'm wrong, how can animals tell if the noise around them is other animals or if it's just what we would call noise? Is that awesome? Yeah, they can. So there have been playback studies where you can play the calls of an introduced species of bird, so something that shouldn't be there, and the birds will react almost as if something's encroaching on their territory. Whereas you can play human-generated noises, and it's more sort of like a fear response. They're not really sure what to do. They're not sure what it is that they're dealing with. They just know it's something that's impacting them. So, yeah, they can absolutely tell the difference between an animal and something else that's going on. They just don't necessarily know what that something else is, if that makes sense.
All right, that's probably it for questions, but I'll give you a chance to play through those videos that didn't work before.
Yeah. Where were we? Yeah. Yeah, so the lyrebird, I think, was the one. So just for context, one of the lions escaped like the inner enclosure at Taronga Zoo, so it had the evacuation alarm. The lyrebirds are really good at hearing human-generated noises and then putting them into their song. So if anyone's watched David Attenborough and there was a lyrebird making chainsaw noises, that's actually how the authorities realised there was unlawful logging in that forest. So, yeah, I know, dibber-dobber, right? So this is what this bird did. It heard the siren. It would wait until there were large groups of people walking past. And, yeah. You can imagine he didn't do wonders for their revenue in those few weeks. Yeah. And yeah, the spiders. Apologies to anyone that's arachnophobic.